So the second calculus-based thing associated with rotary motion is associated with calculating the torque. Because torque is a vector. In our algebra-based world, we just treat torque as a number with a sign, where counterclockwise is positive and clockwise is negative. But in our three-dimensional calculus world, when we use Newton's second law, we still have that the sum of the torques is equal to the moment of inertia times the angular acceleration. Turns out both of the torque and the angular acceleration are vectors. So let's just show something here. So if I have, here's a coordinate system, and let's say I have a vector, radius vector, that goes up here like that. So this is my radius vector. And I'm going to say the radius vector is equal to, and I'm just doing this in 2 dimensions, so we're going to have, let's say that's 6 units and that's 4 units. So the radius vector is going to be 6I hat plus 4j hat. So what we're doing is we're breaking up the radius vector into 2 components, which is the x component and the y component. And the vector addition of those 2 components gives us the resultant vector. And remember, I and j are unit vectors in the coordinate direction. So the unit vector here is, I is a horizontal vector. It's 1 unit long, pointing from left to right. The j unit vector is a unit vector, meaning it has a magnitude of 1, pointing in the positive y direction. Okay, now let's say we want to apply a force out here. Now the force is going to have, it's still a vector, but it's, this is a space vector, so this is really somewhat different. But let's say, let me actually point this a little bit like that. So this is my force vector, which has different scaling factors. So what I may say is the force vector is going to equal to, let's see, it's going to have a negative x component. So I'm going to say it's negative 10 newtons I, and it's going to have a positive y component. So let me draw my dash line. So that's my f sub x, and that's my f sub y. It's not, don't use this scale to determine it. You have to just kind of specify it. So since this one's longer than that, I'm going to say that's negative 10 plus 7 newtons j. And really this would be 6 meters. Well, we have to give some units to them, but I said it in meters. Let's go ahead and do that. So let's say it's 6 meters I plus 4 meters j. So we have these represent meters instead of just numbers. Okay, so in algebra-based physics, what we did was we looked at the angle between, so if I took this radius vector and I extended it, and I looked at this angle here, theta, the torque was this magnitude, like this vector, times the magnitude of the force times the sine of the angle theta. So that's what we did algebra-based. Okay, so what's different calculus-based? Well, the torque vector is equal to the force vector crossed with the r vector. So here's our r vector, here's our f vector. Now what we've done in the past, if you remember, we had something else before which we called the dot product. And we said the work, which is a scalar, was the force vector dotted with this dr vector differential vector that goes in the path of the movement of the object. So this was a dot product. And this is called a cross product because we use a cross instead of a dot. It's also called a vector product. So let's talk in general about how you get the answer. And notice here, cross product of two vectors gives you a vector, whereas a dot product of two vectors gives you a scalar. So this one's a vector. You could also, this is also called a scalar product because you get a scalar out of it when you use this approach. Two vectors give you a scalar here, two vectors give you a vector. Okay, so how do we do this? Well, let's say we have two vectors. Let's say it's A. Vector A is made up of A sub x times the unit vector in the x direction, A sub y times j hat, which is the unit vector in the y direction, and A sub z, which is the magnitude of the vector, and this is the direction of the unit vector in the z direction. And let's say we have vector B. It's another general vector, which is going to give you B sub x times I plus B sub y times j plus B sub z times k. Another way we could, another way to represent vector A is this way. Uses kind of a less than-ish looking sign, and you just list the three components, magnitudes. So if you saw this, you could then, okay, that means that. So it's kind of like a Cartesian pair kind of thing, but it's not a point in space, it's a vector. And you can have the same thing here happening with your vector B. Okay, so how do you find the cross product? Well, we use something that we learned in pre-calculus. And so to find the, let's say we want A cross B. And it's important which is first. Which is you make up a determinant. And the determinant consists of the unit vectors in the three directions, the x, y, and z direction. And then you have A sub x, A sub y, A sub z. So it's kind of like a matrix, but it's not really a matrix. What they're doing is just using this thing that people are used to using and using it to represent how you come up with a cross product. So in algebra, pardon me, pre-calculus, when you learned about a 3x3 matrix and you want to find the determinant, what you would do is you would take this, okay, so this is our determinant. So the way it works is you take this column, or this row, and then you multiply it by the determinant of what's left over if you mark out the corresponding row and column that are associated with this unit vector. So we take I hat, which is the unit vector, and then we write this 2x2 determinant, which you cross this out and you cross that out, and you're left with A sub y, A sub z, B sub y, B sub z. Okay, now the next one is a negative because of the way you calculate determinants. So it's negative j. You cross out this row and this column, and you see you end up with A sub x, A sub z, B sub x, B sub z. And then finally, you get plus the unit vector in the k direction times marking this row out and this column out. You have A sub x, A sub y, B sub x, B sub y. Now all these numbers, A, B's, A's and B's, this row and this row are numbers. So you're going to get you're going to get a numerical value out of these calculations. And then you multiply them by the unit vector, which will ultimately end up giving you a vector. Now, if you remember to do these determinants, you take this times that, and then you subtract this times that. So you'll have a sub y times b sub z minus a sub z times b sub y. So that's this vector. Then you get minus j times the cross multiplication. So you get a sub x, b sub z minus a sub z, b sub x, and finally plus k unit vector times a sub x, b sub y minus a sub y, b sub x. So in three-dimensional sense, that's the cross product. So if we go back to our example here, we have just I and j components, and if you look at that, the only part of this cross product result is this one, because there is no b sub z and there's no a sub z and there's no b sub z or a sub z. So these terms go to 0 for the two-dimensional case, and the torque vector is actually perpendicular to both of those, so it would be either in or out from the screen. So if I want to find the torque, in this case the torque vector for our example, you're going to have the vector, the force vector, which is negative 10 newtons I, and then you have comma 7 newtons J, and that's going to be crossed with the radius vector, which is going to be 6 meters I plus 4 meters J. So using the result that we got a couple of pages ago, what you're going to do is you're going to take, so what we'll have is we'll have the k vector, which is going to be the result when you cross I and j's with each other, you get k, and then this is a sub x. Let's go back and see what we did. So you had a sub x, b sub y, a sub x. So this is a, so you'll have negative 10 newtons, a sub x times b sub y, which is 4 meters, and then you subtract 7 newtons, which is the b sub x times a sub y. So those two multiplications are going to give you numbers, and so we get the torque vector is, okay, let me find my calculator. And so I don't have to deal with sines or cosines or any angles, I just have to do this cross product. So you get negative 10 times 40 minus 7 times 6. And so I get negative 82. Negative 82K. So that's the magnitude of the torque vector. This is the direction of the torque vector. So what you got basically is you've got your x direction here, you've got your y direction there, and then you've got your z direction, depending upon whether you define z out or in. If z's in like that, that's positive, then the torque vector would be actually in this direction in a three-dimensional sense. It would have a magnitude of 82 units going the opposite direction of whatever I define as positive z. And there's a rule, it's called the right-hand rule, which allows you to figure out which direction the vector is going. And what you do is you take your hand in the direction of the force vector, and then you curl your hand in the direction of the radius vector, and then you put your finger and it'll give you the direction, which turns out to be negative in this case. It's hard to do in a two-dimensional sense. I may talk to you guys in class about that, how to use the right-hand rule. So going back to our diagram here, what we would see is that this would cause a clockwise torque, and which counterclockwise torque, which is negative. Yeah. So that bothers me a little bit. But, I got a negative here, and I would have thought that would have been positive. If I take my, so actually the reason it is, sorry about that, it's actually the other way around. So that, if I do that, if you change the direction, so it's R cross F. Okay, so that would make that positive because these are switch signs if you do the opposite order. So it's not F cross R, it's R cross F, which gives you positive, which is what I would have expected from using the knowledge of the right-hand rule and just our knowledge of algebra-based physics, that we would get a counterclockwise torque. So if I hadn't done that, I wouldn't have realized that I had these the wrong direction. Okay, so as far as homework is concerned that involves this is chapter 11. And so let me make sure I'm in the right book here, the right edition. So this is page 295, and what I want you to do is problem 7 and number 10. And number 13. So those are the calculus-based version. And that reminds me, there's some additional thing. There's also, you can figure out the angle, because they ask on problem number 7, it says, find the cross product and the angle between A and B. Okay, so the angle, you actually have to go back to using the dot product. So if you remember the angle between two vectors, and that would be in whatever chapter talks about work. So let me go find that, because I don't remember. Let's see if I can remember what it was. I think what it was A dot B. If you have two vectors, A and B, you dot them together. What you get is the magnitude of A times the magnitude of B times the cosine of the angle between them. So if you want to find the angle, you can find the cosine of the angle by taking the dot product of the two vectors divided by the magnitude of the two vectors. And they'll give you the cosine of the angle. And then to find the angle, you just take the inverse cosine of the cosine. So you calculate this, and then you take the inverse cosine of that. And let's see if I can find the part about dot products. Let me just pause for a second. Okay, so you can see that it's on page 160. And it's equation 7.2. They don't have it actually solved with the cosine of theta, but you can't find the cosine by using this result. So the two vectors are going to be the r vector and the force vector. And so you can find the magnitude by taking the square of the components and adding them together. And then, so that's how you find the magnitude of the vectors. And then the dot product is you have to go back and study that. So I'll let you figure that one out.